All right, welcome back. Let's talk about a second type of rock, sedimentary rock. So sedimentary rocks form from deposited, compacted, and naturally cemented sediments. There are a variety of sediments: sand, silt, clay, pebbles. So a piece of sediment is any piece of rock that's been broken off, however big or small. So for instance, you get sand. You deposit it in a certain area. It becomes compacted. It becomes squished as more and more, for instance, sand builds up. So the sand at the bottom kind of gets squished together, compacted together, and then naturally cemented together with different, as water and different minerals kind of percolate through that sediment, it will cement those things together. So you need sediment that's deposited, compacted, and then naturally cemented together. So these form under conditions of low pressure and low temperature near the surface. I say that because metamorphic rocks are a little different. This is probably the biggest key point and in the biggest part of the story that these rocks tell is that most, not all, most of the world's sedimentary rocks form as layers in or near the shallow parts of the ocean. So if you're looking at a sedimentary rock, for instance, if you go to the Grand Canyon and you look at all those are all layers of sedimentary rock. They're deposited, compacted, naturally cemented together from loose sediment, now forms a good solid rock. So if you're at the Grand Canyon, for almost all of those layers are sedimentary rock. What that indicates is that almost all those layers formed in the shallow parts of the ocean. Therefore, as the different layers of the Grand Canyon was being deposited and turned into stone, that tells us that the oceans had to have covered that part of Arizona. That's how those rocks form. So it's all part of the story. So the whole process of taking sediment and turning it into rock is called lithification. Lithification turns sediment into rock. So you get the deposition of sediment. That material is compacted, squished together, and then once it's squished together, it's cemented together as groundwater flowing through that area will deposit other minerals to help them bind together or facilitate that binding together, cementing them together. So it's not so much what the mineral content of the sediment is that determines the type of sedimentary rock. It's actually the size of the sediment. So if you have big pieces of broken down rock that get cemented together, like gravel, like that makes up, a lot of front yards in Arizona, they have that rock stuff, or around campus, and it's pretty much all gravel. If that was compacted and cemented together, it would form a type of sedimentary rock called a conglomerate, or maybe even a breccia. Sand-sized particles, sand isn't a particular substance, it's a size of sediment. That's what sand is. So sand-sized particles, when lithified, turns to sandstone. Silt-sized particles, which are a little smaller than sand, form siltstone when lithified. Even smaller than silt is clay-sized particles, very powdery. When clay material is lithified, it turns to a sedimentary rock called shale. So what are we looking for with sedimentary rocks? Large clasts or pieces that got, cemented together. So these all look like they're different pieces that got kind of cemented together. We're looking for rocks that are sometimes gritty, very gritty to touch. Feels like sandpaper. Sometimes they exhibit layering and flaking off in layers. Sometimes, not always. So we might see some layeredness to kind of the rock structure itself, or it looks like layers or bands in the rock itself. But it also, again, might have that gritty feel to it. And then also fossils. Most fossils you're going to find are going to be in sedimentary rocks. So that's another thing. Oh, this rock has a fossil in it. Oh, it must be a sedimentary rock. So what do they indicate? Sorry, there was a little hiccup there. My apologies. So what do sedimentary rocks indicate? Well, they can indicate climate change. Different types of sedimentary rocks form in a little bit different types of environments, And typically, if you get a different environment, you get a different climate. So they can indicate climate change, mass extinction. Again, we see a lot of fossils in sedimentary rocks. It's pretty much where we find fossils, so we can figure out mass extinction events. Landslides, if you get a bunch of material flowing downhill and it builds up, and over time, for millions of years, if it gets buried more and more, then this landslide material, the sediment, can turn into stone, so we can see kind of landslide structures. Flooding will also kind of bring in different sediments, deposit them, and we can see those in the rock records, so floods. As well as a tectonic uplift again. Well, if most of these rocks form below the ocean, but now they're not, for instance, the Grand Canyon, if those formed below the shallows of the ocean, and now the Grand Canyon is like 5,000 feet above sea level, or more, I don't know the exact number, how did it get there? Well, tectonic uplift. Somehow that area got pushed up thousands of feet. And these are kind of what we see when we're looking for different sedimentary rocks. Again, pieces, grittiness, layering. Sometimes, here's another fun one. If you're not sure if a rock is gritty, like feels like sandpaper or not, throw it in your mouth and just grind it on your teeth a little bit. You'll find out real quick whether it's gritty or not. Done that one too. Speaking of 2, let me give you another part of the super secret code. It is the number 2. One more time, the number 2. I'll say it again, the number 2. And finally, metamorphic rocks. So these are altered existing rocks that are altered by exposure to high heat, high pressure, or both. Sedimentary rocks get that way because of low heat and low pressure. Metamorphic rocks are an existing rock that morphs, changes, but that's due to high heat or high pressure. Not so much heat that it melts. Then we'd be getting back into the igneous part of the rock cycle. But heating up enough to where it can kind of stretch and get mushed and change a little bit, but not melt completely. This is caused by igneous intrusion. So let's say you get this igneous material cutting up through some layers of the earth. Well, the rock that's next to it are going to get heated up, and they might change. They might morph a little bit. At convergent boundaries, we have a lot of pressure and heat, so that can cause metamorphic rocks. Or as material further gets buried and increases in depth, the more stuff you build on top of other rock layers, the more the stuff below increases in pressure and or temperature. That can help cause and create metamorphic rocks. Or large-scale impacts. When something from space hits the ground, that's a lot of pressure, a lot of heat, and in that just immediate vicinity, you can get some rocks that have been metamorphosed, changed from one thing to the next. So again, just an example of kind of all of these igneous intrusions, convergent boundaries. So you get some magma, some liquid molten rock around it. That heat kind of radiates out, and as this magma comes into contact with the surrounding rock, it will change, metamorphose that surrounding rock that it comes into contact. So it's called contact metamorphism, really close to and around those intruding bodies. You also get convergent boundaries, crustal compression. Well, that was a hard one to say. Crustal compression causes large-scale regional metamorphism, rocks undergoing a lot of heat, a lot of pressure in a big area, so you get regional metamorphism. Again, if you bury under layers and layers of material, that can increase heat and pressure and metamorphose some material. And then impacts. You get some large asteroid impact from space, kind of bam, hits into Earth, and it can alter the minerals and rocks in and around the impact site. So you can get different type of shocked rocks or different types of metamorphosed rocks. Shocked gneiss, impact breccia, swavite, a number of different things. So you can alter material because of an impact. So what to look for? So what you're looking for is foliation. This isn't layers. Okay, this is tricky. This isn't layers of rock. This is mineral banding. This is bands of the minerals kind of just forming different lines. They're banding together. They're not forming different layers. These weren't deposited different layers like sedimentary rocks, but they form these bands. It's called foliation. So kind of like zebra stripes, sometimes these weird mushy stripes. That's kind of what you're looking for. Squished or elongated grains, almost look like stretched Play-Doh. All right, that's material that's being stretched. That's material that's undergone metamorphosis because there was enough heat to allow that to stretch instead of just getting pulled and broken. Sometimes they're very shiny and sparkly. Metamorphic rocks are, they're fun to look at. They're very shiny and sparkly. So something to also, that might indicate metamorphic rocks. You just got to be careful you're not looking at a mineral that's shiny and sparkly. Got to be careful. So what do they indicate? Convergent boundaries, impact events, tectonic uplift. You can, and also, I forgot to put it on here, but magmatic intrusion, volcanic activity can also be indicated by metamorphic rocks, because as magma kind of bubbles up through the crust, it can change the existing rock that's in contact with that that hot magma area. So it can indicate movement of hot molten material. Metamorphic rocks, again, you got these banding. Sometimes they're shiny. It's banding. Sometimes it looks like they're kind of stretched out. So it's the story of rocks, not necessarily the names of them, but what stories can we infer from them? Okay. So again, igneous rocks. What are we looking for? What do they indicate? Sedimentary rocks. What do they look like? What do they indicate? Metamorphic rocks. What is some of the characteristics of them, and what do they indicate? Not that we necessarily need to know their names. We'll learn some in class, but it's more so just analyzing the characteristics of it and telling the story from that. If that makes sense. All right. So that brings us to the end. So again, the rock cycle. So typically we start on the cycle when discussing rocks. Hot magma. If that material cools below ground, forms intrusive igneous rock. If that molten material makes its way to the surface, it's now known as lava and is known as an extrusive igneous rock. If you take that extrusive igneous rock, expose it to the elements, weather, sunshine, a number of different processes on the surface, it undergoes weathering, which means broken down, and then transportation. So we can break down igneous rocks and move that material, erode that material, deposit it, and if it undergoes lithification, it turns into sedimentary rocks. And then if sedimentary rocks undergo more heat and more pressure, they can turn it into metamorphic rocks. And if there's too much heat, too much pressure, then those metamorphic rocks can melt, creating magma, and that cycle starts all over again. But again, it can go any which way. We can start at metamorphic rocks and go to sedimentary rocks, which make more sedimentary rocks, which make more sedimentary rocks, which can go straight to igneous rocks, which can be converted to metamorphic rocks. So Earth is the great recycler. So all rocks are recycled from one thing kind of to the next. Well, that's all I got to say about that. It's been my honor. It's been my pleasure. We'll look at some of these different rocks in class, and we will name some as well, but it's more so the story that they tell. What can we infer from this stuff? Until next time, I'll see you then.